In this video for Computer Science 9618 A-Level, we're going to be taking a look at Paper 3 past exam questions. These questions are going to focus on main memory management. In the video I did just a couple days ago, we got the gist or main understanding or the main points of how main memory management works. Now it's time to put it all together and look at those past exam questions and put them into use. So let's take a look at the first question we have here. Virtual memory, paging, and segmentation are used in memory management. We know right away we'll be able to answer these questions without a problem because we just looked at that video, we studied, and we're ready. Explain what is meant by virtual memory. This is a question you definitely want on the exam. Notice it's worth 3 marks. That is just under 5% of the total points you can earn on the Cambridge exam, and it's an easy 3 points to pick up. So virtual memory is created temporarily. It's not always there. Remember, when a process which is a program running, it's going to reserve more RAM than what is needed. And when it goes beyond the capacity of the RAM, the hard drive is going to be used to expand that memory beyond what the RAM can hold. Now, when the RAM is full, data is swapped between the RAM and the virtual memory as needed. And we talked about that. And when it happens continuously, remember, we said it's going to slow down the performance and disk thrashing can occur. Now, we don't need to list that here because it doesn't ask us about that at all. We only need to say what virtual memory is and how it works. Then let's take a look at part B. State one difference between paging and segmentation and the way memory is divided. And there's really only one way. In paging, memory is allocated into fixed size blocks. We said all of them are the same size, where in segmentation, the memory is allocated into segments of varying sizes. We said paging is static, while segmentation is dynamic. Let's go ahead and take a look at another sample of past exam questions that we can encounter. And here's an example of another one. So main memory is divided into equal size blocks. Because I know it says equal size blocks, I know they're talking about paging memory, called page frames. See? Paging memory. Each process that is executed is divided into blocks of the same size, called pages. Each process has a page table that is used to manage the pages of this process. So we look at this table they've given us, and we know that we know everything about main memory, and we're ready, and we can go ahead and read this table without being told anything. So here I see we have 6 pages, and then it goes on, not showing us the rest, and we have presence flag. What does the presence flag mean? It means whether or not it's currently on the main memory. If I look at page 1, page 2, page 3, and page 5, I can see it's on the main memory. Page 1 has a page frame address of 132. Page 2 has a page frame address of 245. But what does that mean? Well, that's where on the RAM or the main memory where it's currently located. Because it's on the main memory, it has to be located at a specific spot from the start of the RAM. So here, page 3 has a page frame address of 232. We know it's the 232nd page frame from the start of the memory. That's where these numbers come from, how far from the start of the memory it is. Now, if you look at page 4 and page 6, you'll notice they don't have a page frame address. It's 0. Why do they have a page frame address of 0? Because their presence flag is 0. They're not on the main memory. Well, if they're not on the main memory, where are they? They're most likely on the secondary memory, such as the hard drive. Now, because they're not on the main memory, they don't have a page frame address. Now that we know that information, let's go ahead and take a look at the questions that we should be able to answer. The page frame address entry for page 2 is 245. State what the value 245 could represent. Not a problem. We look at it, page 2, it's currently on the memory, page frame address 245. We can't say it's on the memory because they're asking about what the value 245 means. Well, that's where on the RAM it's located. It is the 245th page frame from the start of the memory for this process. Now, do not say it has a page frame address of 245. You're just restating what is there. Cambridge is going to write NE, which stands for not enough. So you want to say it's the 245th page frame from the start of the memory, and they'll give you the full marks for that question. Now, process X executes until the next instruction is the first instruction in page 4. Page 4 is not currently in main memory. State a hardware device that could be storing this page. Well, if it's not on the main memory, where else could it be? Maybe we need to do some memory swapping. So we know it's not on the main memory, somewhere on a type of secondary memory, such as a solid state drive or hard disk drive. That's probably where it's going to be, and we're going to need to swap that out later on if it's ever used by the process. So when we talk about the page frame address, we're talking about the frame number. So right here at the top is the start of the memory. You'll see page 1 has a page frame address of 2. It is the second frame from the start of the memory. Page 4 has a page frame address of 4. Page 2 has a page frame address of 6. Page 3 has a page frame address of 8. So if you're wondering, where did this frame number come from? We talked about it in the video, and we talked about how the logical memory is pointing to the page table, and the page table is pointing to where it's actually stored on that main memory. Let's take a look at the next one. Part C. When an instruction to be accessed is not present in main memory, its page must be loaded into a page frame. Yep, it needs a spot to go on the RAM. So when it says it needs a page frame, it needs a spot on the RAM to go. If all page frames are currently in use, the contents of a page frame will be overwritten with this new page. The page that is to be replaced is determined by a page replacement algorithm. One possible algorithm is to replace the page that has been resident in memory for the longest time, and that is the key. They want to replace the page that has been in the main memory for the longest amount of time. Well, how in the world are you supposed to know which one has been on there the longest amount of time? What additional data would you need? You would need to know what time it entered the memory. If everything has a time entry on the main memory, we are able to compare those times and see which one has been used the longest. So that's what we need, is the time that it entered the memory, because you're going to be comparing time. Nothing else is going to allow us to determine which one has been in there the longest amount of time. Which brings us to this question. Complete the table entries below to show what happens when page 4 is swapped into main memory. Assume that page 5 is the one to be replaced. In the final column, give an example of the data you identified in part C1. Well, what did we just identify? We said what time it entered the memory. So we're going to need to give an example of that. I look at page 5 as it has a presence flag of 1 and the page frame address 542. And that is what I need. I know page 4 is being swapped in to main memory. That means its presence flag is going to become a 1. What is its page frame address? Well, it's replacing page 5. So it's going to have a page frame address of 542. Now, the additional data, when you go to put the time, remember, computers work on hours, minutes, seconds, and milliseconds. If you've ever used a timer in a high-level language, and if you're on paper 3, you most likely have. And you know when you use a timer in a high-level language that it works based on milliseconds and not seconds. So you have to put the hour, the minutes, the seconds, and the milliseconds. So just put a valid number. The one I put down was 10:37 a.m., 59 seconds, 41 milliseconds. You must have 4 values, not just 3. So make sure if you see a question like that, you put all 4 values, because computers work on milliseconds, not seconds. An alternative algorithm is to replace the page that has been used least. Give the different additional data that the page table would now need to store. Knowing the time that it entered doesn't even remotely tell us how many times it has been used. It says give the different additional data. Well, of course we have to give different additional data, because time doesn't tell us how many times it's been accessed. So how do we know how many times it's been accessed? We give it a counter. We need to know how many times that page has been accessed. Once we know that, we know which page has been used the least. The only difference is, instead of comparing time, we're going to be comparing how many times that page has been accessed. So nothing too complicated there. In the following table, complete the missing data to show what happens when page 3 is swapped in the main memory. Assume that page 1 is the one to be replaced. In the final column, give an example of the data you identified in part C3. So page 3 is being swapped in the main memory. That means its presence flag is going to have a 1. I need to look at the page 1 data. Page 3 is going on the main memory. Presence flag is a 1. I picked up 1 point. It's replacing page 1. What's the page frame address for page 1? That's 132. Then I need to know how many times it's been accessed. Now you may be saying, oh, as long as I write a number like 87, I'm good to go. Just slow down 1 second because it's not that simple. Page 3 just got swapped in to the main memory. Because it just got swapped in, how many times has it been accessed by the main memory? 0 times. It's been accessed, or by the process. Because it just got onto the main memory, hasn't been accessed at all. It starts with an access number of 0. That's how many times it has been accessed. So you want to watch out for that and be very careful. And this leads us into our last 2 questions about time and the one least used. Explain why the algorithms given in part C may not be the best choice for efficient memory management. Well, what about the longest resident? Why is that not efficient if it's the longest resident? Well, it may have been loaded onto the RAM early. It may have been one of the first things used by the process and loaded early. I mean, you have to start somewhere loading things onto the RAM. There has to be a piece that goes first. Maybe it was loaded onto the RAM early. But just because it's been on the RAM the longest, that doesn't mean is it currently being used or needed by the process that it's currently executing. It may be being accessed frequently and very often. So just because it's the longest resident doesn't mean it doesn't need to be used. If it's being used frequently and often, I'm going to have to switch it from the main memory to the hard drive and then back from the hard drive to the main memory, back and forth, back and forth, back and forth. This is going to bring the performance of my computer speed way down and also cause disk thrashing, which could cause my hard drive to fail prematurely. What about if it's the least used? Well, this ties back in to the question we just answered. It's not good for data that just entered the memory. If the data or the page just entered the memory, it will have a value of 0 for how many times it has been accessed. We just put it on there. It hasn't had a chance to be accessed. So if it least used was the algorithm, the data just swapped in would immediately be swapped out. Back and forth, back and forth, back and forth. That's going to lead to poor speed performance and lead to disk thrashing. Hope you guys found this video helpful. If you did, make sure to give it a thumbs up and subscribe to help the channel grow. And we'll see you guys in the next computer science video.